Hello, very welcome back to our channel. And on your screen, we have one new problem statement. So let us try to understand and see how we can solve this problem. So the problem statement has given us this circuitry here that consists of one diode and couple of resistors. And it has got an input voltage source, Vs, that has a signal of this form. So it is basically a square wave with a peak amplitude of +8 volt and -10 volts. And one time period of this signal is from this end to this end. Okay, so here is your t by 2 and here is your t. So the total time period here is t. And frequency of that signal obviously 1 over t, as can be understood. So now it says in this circuit, Vs is a square wave of period t with maximum and minimum values given. So maximum value is +8 volt, minimum value is -10 volt, respectively. So diode is assumed to be ideal. So when we say this diode, it is an ideal diode which doesn't have any turn on voltage, which is commonly found in the practical diodes of silicon, germanium, etc. They have their minimum threshold voltage, which the external voltage applied needs to overcome in order to make it on. And the resistor values are given, each R1 and R2 about 50 ohm. Okay, and we have to calculate the output voltage VL, that is the voltage across R2, which is acting as a load here. That's why we call it as a load voltage. We can also call it as a V2, or let's say VR2, or simply VO, whatever you prefer. So currently we have VL notation here. So how to understand and solve this problem? So it is pretty simple. If you have a look at this waveform, so you are given a positive half cycle and then the negative half cycle. So during the positive half cycle of this circuit, we see the positive makes this diode reverse bias. So obviously this diode is not conducting. So we can draw this circuit again for the positive half cycle. Let me write here positive half cycle. Okay, and the circuit will look like you have this resistor and the diode has open circuited. R1 is here, and then you have this second resistor R2 across which we are measuring the load voltage RL right over here. And what we see from this case, R1 and R2 both are 50 ohms each. Therefore, voltage VL would be equal to, due to voltage division, R2 multiplied by Vs. Here is your Vs divided by R1 plus R2. So obviously, we know that it would be 50 multiplied by Vs divided by 50 plus 50. So this comes out to be Vs divided by 2. So the voltage, maximum voltage is +8 volt and it has got like 4 volt because Vs is 8 volts. So for the waveform, we can draw the waveform here again. So it would be like this. You have this time scale on the x-axis and you have got this voltage. So here you have now this time period. We can draw this as in the given waveform. So that we can actually relate to that. So here you will have the 4 volt amplitude. So let's write it here. Okay. And now let us see what will be the output for the negative half cycle. So for the negative half cycle, we see here, let me use here, you will have the negative coming here, making this diode forward bias. So we can write and draw the circuit like this again. So forward bias, the diode is set to be ideal, so it acts as a closed switch. Here it acts as an open circuit. Here it acts as a short circuit, SC short circuit, OC open circuit. And here you have this voltage source Vs. Again, let me write it R1. And here you have this resistor R2 across which you are measuring the load voltage. And you see here, the load voltage in that case would be this resistor is effectively short circuited due to this short circuit here. So essentially, your circuit is further simplified to Vs, and then this is a short, and this is your, here we can write R2, and that's your the load voltage, final load voltage. So obviously this Vs appears across R2. So VL is going to be Vs, which is minus 10 volt. Okay, because Vs is here minus 10 volt during the negative half cycle. So we can draw in the output. This is the load voltage VL. Okay, this is the Vs waveform, and this is the output voltage waveform. So here you have this minus 10 volt somewhere here, and that's your amplitude. And then again, after the positive half cycle comes, the cycle repeats, and that's how you have it. And the situation continues like this. So the output voltage VL is plus 4 volt and minus 10 volt. So that is how it appears. Now, the question here is we have to compute or calculate the average value actually. So the question here is how we compute the average value of the output signal Vs. So we can write the average value of VL will be equal to the area of this curve, that is plus 4 volt. So area would be area under the curve divided by the time period, time t. So we can write the area is 4 multiplied by this is t by 2 here, right? And here is again t. So here is t by 2. So we can write here, let's say t over 2 plus the area of this waveform can be computed again by the amplitude multiplied by the time, right? So here is minus 10 volt multiplied by again t minus of t by 2. So from t to t by 2, this time period actually is again t by 2. Okay, so here is this term is 2t minus t divided by 2. So it will be t by 2 again. So like I said, so divided by the total time period is t. That is from this end to this end. And this would be then 40 by 2. So it would be 2t, that is 40 by 2, that is 2t. And here it would be minus 10 into t by 2. So it would be like plus 5 or 2. No, not the plus, but it would be minus actually. Minus 5t, right? Because this term is here minus t, minus 10 into t by 2. So it will be minus 5t. Okay, so that is correct. And then this is 1. And here it is this minus 3 by 2 divided by t. So t gets cancelled. The answer is minus 3 volts. This is the average value of this waveform. So this is the average value of this waveform, and this is how we could solve this problem. So hope you found this module useful. If you did so, you can click the like button, share with others for the wider reach, and stay tuned for more engaging content like this, which you have been learning.